Okay, today I would like to talk about the working principle of the MOT. MOT, aka magneto-optical trap. MOT plays the key role in most of the cold atom experiment because this is the first step of capture and cool the lasers, cool the atoms from the room temperature to a few hundred microkelvins. To address this issue very clearly, I would like to talk about 6 aspects. First, it is the light polarization. That is the O part, which is the optical. And here I would like to emphasize on circularly polarized light. And after talk about the optical part, I would like to talk about the magnetic part, which is the quadripolar magnetic field. That is formed by the anti-Helmholtz coil pairs. Thirdly, once we give the B field, we can define the quantization axis of the atoms, and therefore I would like to talk about the quantization axis and the sigma plus and sigma minus transitions. How does this related to our MOT configurations? Once we have all these 3 components, we can then talk about the conventional 6-beam MOT. And another conventional configuration for forming the MOT is also very popular, that is 3-beam. But here we need to use retroreflect configuration because we do need the counterpropagate beam to cool the atoms from both directions. And then I will talk about the pyramid MOT, which is in our case how to form the pyramid MOT. Okay, then let's begin. First of all, the polarization, the light polarization. I would like to add some photos. Okay. In this figure, we know the light is propagate along this axis. I call it Z. And the light propagating direction, we call it K vector. K is wave vector. That defines the propagation direction of the light. And these small arrows is the electromagnetic it's a electric field direction. as you can see, along the propagation direction, it is not fixed. It is actually rotating along the z-axis, along the k vector. And we call this scenario to be the circularly polarized light. And how to define the handiness of the light? We need to sit on the observer side. Let's say the light propagating in this direction, and we need to put our eye here. We look into the beam, and we can see in this scenario the light is rotating clockwise. Right? When we observe the light we look into the light, and we can see the light is rotating counterclockwise, because this is the first, second, third, fourth, fifth. This is polarization vector that you receives, and you can see it is actually rotating counterclockwise, and therefore we define the counterclockwise as right hand polarized. Because if you use your right hand and you let k vector follow your thumb, and the forefingers is the direction of the polarization rotates, and you can use the right hand to recover this scenario. Okay, and if this vector rotate clockwise, then we call it left hand polarized. Okay, let's remember this combination. And when you define the light polarizations, circularly polarized light, which handiness you use, you need to always sit as the observer. Okay, then we can talk about the quadrupole. Magnetic field. We're all very familiar with the MOT configuration, where we use a pair of anti-Helmholtz coil. I will not draw the dimensions of these coils for now, because everybody is very familiar with it. Okay. We know that for the anti-Helmholtz coil configuration, the current flow through the two coils are opposite. And if you use the right hand rule, you can figure out what is the magnetic field directions. And in our case, it is like this. And I call this B direction. We know in the center part, the B field cancels, and this B naught equal to 0. And along the, because you can see it is rotating symmetric with respect to z-axis, so we can use cylindrical coordinates to address this problem. Then I define this axis to be z, and this axis is rho, because it is rotating symmetric along z with respect to z-axis. Okay, along the z-axis, we can see the B field strength is getting bigger and bigger in the central region, because it will eventually die when it reach very far. For example, here, this is infinite. Of course, here the B field is 0, right? We only care about this regime where the MOT forms. And along the minus z side, the B field strength also increases, but in another direction. And along the rho axis, the B field decreases when it approaches to the center. Okay, this is how the B field looks like inside, in the central region of the anti-Helmholtz coil pairs. Okay. Then I will make this clearer. I will draw the B field along the rho axis and the z axis separately now. This is B rho, B z, and we can see along the z axis, the B field was negative but big, and then approach to 0, becomes 0, then grow again, and it is linear. This is BZ. For B rho, it is exactly opposite, because for the negative rho, here is negative rho values, and you can see the B field is pointing towards the positive rho. That means it is actually this way. I call this B rho. This is how the B field looks like along the Z and rho axis. Okay. Now we can define the quantization axis. Of the atom. For atom along z-axis, the quantization axis is pointing z is pointing in this way. That follows the B field direction. And for atoms along rho axis, the quantization axis let me use another color. For atoms along the rho axis, you can see the curve is falling down, and that means the quantization axis is exactly opposite. Okay. Now we know the quantization axis of the atoms along the z-axis and the rho axis respectively. This is only half of this chapter. And I would like to give a table that defines how you address sigma plus light, how you address sigma minus light transitions. Because sigma plus, sigma minus is a combination of light polarization and quantization axis. Okay? It is not right-hand polarized light drives sigma plus and left-hand polarized light always drives sigma minus. No, it's not like that. Okay. For example, if you have quantization axis, this is your quantization axis. Let's use the red color to represent the laser beams. Let's say you have the laser propagate along your quantization axis, and it is clockwise. It is a clockwise polarization, which is left-hand polarized. That means the rotation of your electric field is in this way, and this drive sigma plus transition. When you have the light propagate along your quantization axis, but counterclockwise, rotating, which is the right hand polarized. Now, use your right hand, use your thumb to follow the K vector, and the four fingers indicate the polarization rotating. This gonna drive what? Gonna drive sigma minus. Okay. This is a convention notation we need to remember. Okay. Let's say now the light propagate anti-parallel to your quantization axis. We again use left hand first, which is this way. Left hand, and therefore it is clockwise. If you use your left hand, if you hold your left hand up and use your thumb to point into your eyes, and you can see the four fingers follow the clockwise direction, and this is called left hand. And in this case, it's gonna drive sigma minus transition. Okay. The last case, again, light propagate anti-parallel to the quantization axis, but counter-clockwise. Right hand, sigma minus, sigma plus, sorry. Let me draw it correctly. Now, this table is very valuable. Okay. And let's go back. Let's don't forget this one, because now we can talk about the conventional 6-beam MOT. Which is the chapter 4. We already know that along the z-axis, the quantization axis is in this way, and the B field let me copy this here as well. Okay, for the axis, let's first talk about this one. We know the quantization axis is in this way, and before that, let me introduce something else first. To form the MOT, the simplest atom energy level diagram has to be J equal to 0 to J prime equal to 1 transition. Where J is the angular momentum of the atoms. Okay, you can find any, you can find this contact in any atom physics books, textbooks. Here I won't explain this because this is not the key point we need to know for this lectures. Let's say the ground state J equal to 0 and excited state J equal to 1, J prime equal to 1 prime. And you know, because we have the B field, that means the Zeeman sublevels inside the J prime 1 prime will be splitted according to the B field strength. And this is Mj prime equal to 0, J prime 1 prime, Mj prime equal to what? This equal to what? We know let me use a dashed line as a helper line to illustrate. Let's say this is a point. Here is another line. Okay. This is point A, this is point B. Okay. At point A, we know B field is positive, and therefore this is 1. And thereby this is -1. Okay, I will erase this part. Okay, this is point A, point B. Okay, you know, when we shine the MOT beam, that is usually red detuned light because of the Doppler effect. Let's say this is our laser field. Laser is from J equal to 0 to J prime equal to 1 prime, red detuned. Okay. And now we can see for example, if the atoms have the velocity in this way, we want to accelerate the atoms in that direction, right? And we expect the atoms to absorb the light from this direction, right? And if the laser is this frequency, let's say this frequency, it hit the 0, mj equal to 0, 0 to -1, and therefore we need a sigma minus light, right? And on the other hand, when atoms have the velocity along the positive z direction, we hope to accelerate the atoms in the opposite direction and move it into the center. And in this scenario, we talk to, sorry, I made a mistake. Here, this line is 1, minus 1, minus 1, 1. So this one should be plus. And for this side, it is this one. And on this side, that is the minus 1. So here, this is sigma minus light. Okay, good. Not so good. Now, let's use this table. Quantization axis, the light from this side drives sigma plus, the light from this side drive sigma minus. Okay, what polarization we need to use in this case? Sigma plus, that is clockwise left hand, which is this case. Left. And the sigma minus, the k vector is opposite to q. We remember this. K vector is opposite to q. And we need sigma minus. Okay, again, left hand. That means what? That means for we need to shine left hand polarized light from both direction, I mean positive z and negative z. We need to shine both sigma, we need to shine both left hand polarized light. And this one can form sigma plus and sigma minus, where this is sigma plus, this is sigma minus light. Okay, here I don't need to do the row axis anymore because it follows the same logic. You're gonna find it out. You need the right hand polarized light from both directions. Right. But it's gonna give you sigma plus and sigma minus from both directions. Okay. Let's say I want to change another color. Let's say use green. Because 6-beam cools atoms in 3 directions. Here, I focus only on one direction. Let's use the axis. This is a counter-propagating light. Let's say 6-beam. Counter-propagating light. You have 2 laser sources from Z and minus Z, and they are both left-hand polarized. So it is this and this, and it can drive sigma plus, sigma minus. Let me double check. Yes, sigma plus and sigma minus. Great. Okay. Now I would like to talk about the 3-beam MOT. When it is 3-beam, there are still 6 beams. When we use 6-beam, we can use 6 laser sources, form 3 pairs of the counter-propagating light along the X, Y, Z axis. For the 3-beam configuration, we have only 3 laser sources that being aligned along the X, Y, Z axis respectively, and we use a retroreflect mirror that is perpendicular to the X, Y, Z axis, such the retroreflect beam form the counterpropagate light to form the MOT. I hope this is clear enough. Okay, when it comes to the 3 beams where we need to use retroreflect mirrors, I would like to talk about how the light polarization being affected by the mirrors. Let's say I have a mirror like this. Okay. Here I have the cloud of the atoms. Let me call it atomic cloud. And they are full of atoms. Let's say I shine the light. This is incident light. Incident light and this is reflected. Here I separate them, but in reality they are overlapped. Okay, I separate this because I want to draw the polarization vectors so it can be demonstrated clearer. Okay, now I will draw the vectors. Let's say it's rotated like this way. First, oh no, okay. This bars, this arrows, dots, arrow, cross refers to the light vector that is rotating along the k-axis. This is k lah. This is k, you know. Okay, if we sit into the beam and we observe what is the polarization in this case. Remember, this is the first k vector you see, second, third, fourth, fifth, sixth, seventh, and blah blah blah, blah blah blah. Okay, and now you can see first it pointing inside the paper and then rotate to 2. Oh, I think I missed something. Or let me redraw this maybe. One, two, three, four, five, six, 7, 8, 9. Okay, let's see. First, it is 1, then 2, 3, 4, 5, 6. We can see it is left hand. It is left hand polarized. Left hand, and when it reflects back, 1 comes first, right? 1 will be reflect first. Count 1, and 2 will be pointing into the paper. 3, 4, 5, 6, 7, 8, 9, blah blah blah. And now we need to see the light in this direction. This is the K. Okay, we can see it is rotating counterclockwise, which means this light is right hand polarized. Right hand polarized. Now, let's say I'm the atom. The light from incident is left hand. From retroreflect is right hand. Can this form the MOT? The answer is no, because we already know they need to be the same handedness from the both sides. Then how to achieve those? We need to flip the polarization of the retroreflect beam. How to do it? We need to add a cautery plate. Let's say this is cautery plate. And therefore, we flip the retroreflect beam by lambda over 2 combine. Then we can have left-handedness again, and therefore give us sigma plus, sigma minus configuration and form the MOT. Okay, this is a tri-beam MOT configuration. I can draw it roughly lah. X, Y, Z. Okay, you have laser beam this way, this way, this way, and you need to have mirror to retroreflect the beam, and before the mirror you need cautery plate to flip the direction of your light. So you can form the MOT here. Okay, now it is the last part, which is the most exciting part. Why we don't need pyramid MOT? Why we don't need cautery plate? Why we don't need this for the pyramid MOT? Okay, here I don't need to analyze the quantization axis anymore, because as long as we figure out the handedness of the light beam, we can know whether it's gonna work or not. Let me first draw a pyramid only in x-axis, let's say. This is a cross section. Let's say this is along the x-axis. We have the light, incoming light. Okay, I will just use the black one, black color. This is the incident light. This is a K vector. And we make it left hand polarized, for example. Left hand. Okay. That means the vector will be like this. Okay, and we all learned the mirror reflection. We can draw some help line. This is 1, 2, 3, 4, 5, 6, 7, 8. Okay. 1, 2. This is 2. Because it's a mirror reflection, this one become this. And the third one, same. Fourth one will be this. 5, 6, 7, 8. Okay, when this beam propagate in this direction, what polarization we get? Let me use another color. This will be the K, and you can see it is this, this 4, 5, 6, 7, 8, and you can clearly see this is a right hand polarized light. A right hand polarized light. Okay, now this light will be bounced off the second mirror, which is this mirror. I call it second one. This is the first mirror. How this gonna work? Again, I will draw the helpline. Okay. 1, 2, 2 become this. 3, 4. For this one. 5, 6, 7, 8. Okay. Now let's look at what is the output light looks like. I will change another color. Let's use green. This is reflected beam. K vector 1, 2, 3, 4, 5, 6, 7, 8. Now we can flip the pad and use our hand to try left, right. Let's see. Oh my god, this is left hand polarized light. Left hand polarized light. So in this scenario, we can already know this. The light coming in and reflect out has the same handedness. Okay? Left, left. That means at least along the z-axis, the polarization is correct. This is z-axis. Maybe I can give a brief drawing of the pyramid. Let's say this is a MOT coil. This is the MOT position. This is rho, z. Okay. Okay. So at least along the z-axis, we have left, left. Okay. And on the along the rho axis, I call it rho. Here you have right. Now what we need to check is the other way around, which is this way. Let's say we have the light in this direction. Okay, we're gonna apply the same technology used in here. Let's do it again, and this is a good practice anyway. incident beam. And we use left hand. Why? Because all the light coming towards the pyramid has the same polarization. Let's see, left hand. Okay. Left hand, so it is this, and we have 1, 2, 3, 4, 5, 6. Left hand. And now we draw the help line. I hope this is helpful. Okay. 1, 2, 3, 4, 5, 6. Okay. This is what, and you can clearly see this reflect is right hand. The green light is left hand. Okay, combine this and this, we can have the conclusion. Right. We can conclude this configuration is valid, and therefore we can form the pyramid MOT without the help of the cautery plate, because it naturally form the left hand counterpropagating and right hand counterpropagating. What we need to do is to choose the right B field directions, which is the current. As long as the current is being chosen correctly, we can form the MOT. Why? Because we need to match the quantization axis. Okay, that's it. I hope this is very clear for everyone to follow. And if you want to have more detailed information, you can always come to me, drop me a message. And I would like to thank these two guys, Akshay and Isaac, for the fruitful discussion about this topic. Thank you.